start our on the topic for comparison, which is we call Heap Management. This is a theoretical topic. Just we will give the introduction about the heap allocation. Is the most flexible allocation scheme. Variables local to process allowed to deallocation only at runtime. Heap allocation uses dynamically allocate memory variables and the client back when variables are not no more requirement. Heap storage allocation supports the recursion process. Heap is a portion of the store that is used for the data that lives infinitely or until the program explicitly deletes it, while local variables typically become inaccessible and the processor end. Many languages enable us to create object or data type whose extension is not tied to processor activation that creates them. Garbage collection is the process of finding spaces within the heap. There are no longer used by the program and can therefore reallocate to house other data items. Language like this, Java, it is a garbage collector that deallocates memory when it is required. The garbage collector is an important subsystem of the memory manager. Memory manager keeps track of all the free space in heap storage at all the times. It performs two basic functions, allocation and deallocation. Allocation, when a program requires memory for a variable or object, the memory manager produces a chunk of continuous heap memory for the requested size. If possible, it satisfies an allocation request using free space in the heap. If no chunk of the needed size available, it seeks to increase the heap storage space by getting consecutive bytes of virtual memory from the operating system. If space is exhausted, the memory manager passes that information back to the application program. Deallocation. The memory manager returns deallocated space to the pool or free space, so it can reuse the space to satisfy other allocation requests. Memory manager typically do not return memory to the operating system. Then, when the programming heap usage drops. All allocation requests are chunks of the same size. Storage were released periodically, says first allocated, first are deallocated. There are some languages such as Lisp for which the condition hold pure Lisp uses only one data element or two pointer to set from which all the structures to build. Condition B. Also, hold the some situation, the most common being data that can be allocated on the runtime stack. However, in most languages, neither A nor B holds it in general. Neither data elements of different sizes are allocated, and there are no good way to predicate the lifetimes of all allocated objects. Properties of memory manager. Space efficiency. The memory manager should minimize the total heap space needed in the program. Doing so allows larger programs to run in a fixed virtual address space. Space efficiency achieved by minimizing fragmentation. So, program efficiency. The memory manager should make good use of memory subsystem to allow the program to faster. The time taken to execute an instruction can vary widely depending on the objects where placed in memory. Fortunately, programs tend to exhibit locality which refers to the non-random trusted way in which typical programs access memory. By attention of the placement of the objects in memory, the memory manager can make better use of the space and hopefully make the program run faster. What is a low overhead? Basically, memory allocation and deallocations are frequent operations in many programs. It is important those operands as efficient as possible. That is, ways to minimize the overhead. The fraction of the execution time spent performing allocation, deallocation time. Notice that the cost of allocation is dominated by small requests. The overhead of the manager managing large objects is less important because it usually can summarized over a large amount of computation. So memory hierarchy. See, the memory hierarchy consists of series of storage elements with smaller, faster ones close to the processor and larger, slower one faster away. See that is a register which is very close to the CPU. Registers, processor close. So 30 bit. It's 1 nanosecond. Within 1 nanosecond, the CPU can access these registers. First level cache. It's a 5 to 10 nanoseconds we can catch. The memory size 16 to 64 KB. The second level catch is a 40 to 60 nanoseconds. It's 120 KB to 4 MB. Physical memory. So 100 to 150 nanoseconds needed to access the physical memory. So it's 250 MB to 2 GB. Virtual memory. So 3 to 15 milliseconds is more than 2 GB virtual memory. So typical sizes, typical access time. This is a memory hierarchy which is very close to the CPU. That's what I explained here. Typically, a processor smaller number of registers, those who want to be under the software control. Next, there's one more level, cache, usually made out of the static RAM, so kilobytes, and several megabytes in the size. Next level hierarchy is physical memory, main memory. Memory made out of hundreds of megabytes or gigabytes of dynamic RAM. So physical memory is there, is then back to virtual memory. It is implemented by the gigabytes of disks. Upon memory access, the machine first looks the data in the lowest level of the storage. If the data is not there, looks at the next level hierarchy, next higher level, and so on. All the other levels of hierarchy are managed automatically. So with the cache memory access, the machine searches each level of the memory in the succession, starting with the lowest level until it locates the data. Caches are managed exclusively in hardware in order to keep up the relatively fast RAM access time. So locality in the programs. Most programs exhibit a high degree of locality. That is, they spend most of their time executing a relatively small fraction of the code and touching only a small fraction of the data. Temporal locality. The program has temporal locality. The memory locations to access likely to be accessed again within the short period of time. Spatial locality. A program has a spatial locality. The memory locations close to the location accessed are likely to be accessed within a short period of time. Programs often contain many instructions that are never executed. Programs built with components libraries use only a small fraction of the provided functionality. Also, as a requirement to change the programs, all legacy systems often contain many instructions that are no longer used. Static and dynamic RAM. Most random access memory is dynamic, which means that to build very small electronic circuits that lose their charge in a short time. When circuits needed to repress, that is, the bits read and rewritten periodically. So, on the other hand, static RAM design, the more complex circuit of each bit, consequently, the bit stored will stay indefinitely until it changed. Eventually, a chip can be store more than bits. If it is used for dynamic RAM circuits, it is used for the static RAM circuits. We need to see large main memories of the dynamic variety, while smaller memories like caches and made from the static circuits. Quality allows us to take advantage of the memory hierarchy of a modern computer by placing the most common instruction, the data, in the fast build small storage, while leaving the rest in the slow but large storage. You can lower the average memory access time of the program significantly, reducing fragmentation. At the beginning of the program execution, the heap is one continuous unit of the free space. As the program allocates and deallocates memory, this space is broken up into free and useful chunks of the memory. And the free chunks are not reside in the continuous area of the heap. Refer to the free chunks of the memory as a wholes with each allocation because the memory manager must place a requested chunk of the memory into a large enough hole. With each deallocation request, freed chunks of the memory are added back to the pool of the free space. We collapse the continuous holes into larger holes as the holes can only get smaller otherwise. If we are not careful, the memory may end up with getting fragmented, consisting of a large number of small, non-continuous holes. And then possible to do that no hole is large enough to satisfy the feature request, even though there may be sufficient aggregate free space. Best fit, next fit object placement. Reduce the fragmentation by controlling how to memory manager places new object in the heap. It has been found empirically that a good strategy of minimizing fragmentation for real live programs to allocate the requested memory in the smallest available pool that is large enough. The best fit algorithm tends to space the large holes to satisfy subsequent larger requirements. An alternative called is a first fit, where an object is placed in the first hole in the which is the fits takes the less time to place objects, but has been found inferior to the best fit in overall performance. To implement a best fit placement more efficiently, we can separate free space into bins according to the sizes. One useful adaptation of the best fit algorithm is to modify the placement in case of when a chunk of the extra request size cannot be found. In this case, we use next fit strategy, trying to allocate the object chunk that has last been split. Whenever enough space for the new objects remains the chunk. Next fit also can improve the speed of the allocation operation. Thank you for listening this unit.